values it depends on. Thank you. And now our tensor x has a property grad, which contains this derivative of y with respect to x. Okay, makes sense. So why is it 10? Because algebraically the derivative of x squared is 2x. 2 times 5, 10. Okay. Behind the scenes, a bit about how this works. So PyTorch has wrappers for tensors, which is variables or high-dimensional variables, vectors. And when we write a computation, it doesn't just calculate the numeric value. It builds an expression tree of that computation. And using some calculus, the chain rule, it can automatically compute the partial derivatives of any result with respect to any other node in the tree. Okay. So how does this help us solve our problem? We can, so let's show a simple solution. We start with preliminaries, imports, and defining the constants that characterize the problem. Then we have our objective function. So this is what we want to minimize. And this is exactly how you would implement it, for example, in NumPy, except that instead of using np.square-root, I'm using torch.square-root so that it's part of the expression tree, which can later be differentiated through. And then we have the gradient descent optimization. So we have an initialization of some initial value. We create an optimizer, which is a PyTorch object that performs the minimization, that performs the you take a small step in the direction of the derivative. And this optimizer is a very simple one, so gradient descent like we saw. But further down the line, we'll see different kinds of optimizers and how they affect the optimization. And then we have a loop of 20 iterations during which we calculate the forward pass. So this is the calculation of the time for the value of x right now. And then we do three steps that together take a gradient descent step. So we reset the optimizer. We use backward to calculate the derivatives, and we use optimizer.step, okay, which actually changes the value of x. Okay, when we created the optimizer, we passed two things. One is the list of parameters that I want to optimize, that I want to change, and the other is LR. LR stands for learning rate. This comes from machine learning terminology, but this is basically what is the step size that I'm going to take. So we have the derivative, and I'm multiplying it by something when I want to take an actual step, an actual change to the parameter. All right? Any questions so far? Yes. Just a moment. We need a microphone. I guess he can use my microphone, right?
Oh, yeah, cool. Yeah.
Thank you. So if we replace, for example, the x declaration by using the NumPy, tensor instead of torch, it doesn't work for the computation graph.
Right. So you ask if we use, for example, NumPy instead of PyTorch, then it wouldn't work because NumPy is just a linear algebra library. It doesn't have wrappers. Or it does have wrappers, but it doesn't support automatic differentiation. So PyTorch takes care of a lot of things behind the scenes of constructing the expression tree and calculating the partial derivatives. Okay. All right. Any more questions? Okay. So when we optimize, we can visualize it in many ways. These are two. So on the right, we have the objective function, the time, that we started with some initial semi-random value. And we see that the time indeed decreases as we want. And on the left, we have the actual path, okay? The path, this is the initial path, which was on the bottom in red. And we see that we slowly converge to a path that is much faster, okay? All right. So that was just optimizing one dimension. In many dimensions, this is pretty much the same. So in terms of code, in terms of concepts, it works very similarly. One thing to notice is that in one dimension, the derivative basically tells me if I increase x, will it go up or down, right? But in multiple dimensions, we don't have a single derivative. We have multiple partial derivatives with respect to each of the parameters that we want to optimize. And the vector of all the partial derivatives is called a gradient. And it tells me like what is the direction of fastest ascent or fastest descent. Okay, this is the negative of the derivative is the direction of fastest descent. So imagine that you're standing on a hill with your eyes closed. You can still feel which is the direction of steepest, that will be hardest for you to go up or most scary for you to fall down. Okay, but the optimization works pretty much the same. So I take a step. My solution is characterized as a vector, and I take a step in the direction of the negative of the derivative, which of the gradient, okay, which is also a vector of the same size. So the first thing that I want you to do, the first exercise, involves taking the problem that we just saw and generalizing it to 2 parameters instead of 1. So now there are 3 terrains. Okay, they are equally spaced, but the dog has different speed on each of the terrains, and we want to find. So now our solution is characterized by 2 variables, right? Where do I cross from the first terrain to the second, and where do I cross from the second to the third? Okay, and we want to find a pair that minimizes the total time. So set up the environment, run Jupyter Notebook, and you can open the example and play with the example, which shows the solution to the 1D problem, and then give the 2D problem a try, and I'll move around and try to help you. Good luck. Also, if you want, you can work in pairs. It can help with if somebody has technical issues installing the environment, and it can also help to brainstorm together and explain to each other. So you're welcome to do it if you want to.
Yeah, the environment will download the torch with CUDA, which most of the time is spent downloading CUDA. I believe one can go and
At
check.
the CPU?
Yes, at the CPU version of Torch, and it will install probably much faster.
Yeah, thank you. That is a good idea. So I'll show what you meant. So you meant like this, right? Yeah, I don't remember. The exact, yeah. I'll check it out now. Yeah, so if anybody's having issues installing, I'll check now how to install specifically CPU PyTorch. Yeah, so I think changing the requirements to torch dash CPU should be at the CPU only. Try it out and I'll move between you and try to help. So pay attention. In order to do visualizations, there are three helper functions that where you can log the history of your optimization loop. So there is reset history and visualize history at the beginning and at the end of the loop, which don't accept parameters. And there is log history, which accepts the time, which is your objective function that you calculate every iteration. It should be a tensor, a single, a scalar tensor, and a tuple of the parameters that you optimize, so x1 and x2. And if you do all of those, then you'll get at the end a visualization of your optimization. And also you need to pick the initial values, so replace the torch none, NaN, with numbers of your choice. And if you're finished, you can. There's like a food for thought at the end of after the exercise, and you can play with the hyperparameters, like with the learning rate, with the initialization, with the number of iterations, and see how that affects the optimization and the results. Who's still working? All right, who's done? Okay, so I think 2 more minutes, and then I'll go over the solution. Okay, so let's quickly go over the solution. So for the implementation part of the objective function of the time, this is a PyTorch translation of the formula above, and it's quite straightforward. So for each of the line segments, we compute the length, we divide by the speed in that respective terrain, and we sum those times together. This time our objective function accepts two parameters, x1 and x2. So this makes it a two-dimensional problem, but it still returns a single scalar that we optimize. And all of those are tensors, so we can automatically differentiate through. And the optimization loop is quite straightforward as well. So I picked some initial values for x1 and x2, and we created an optimizer. You'll notice that the learning rate, the step size is different from the previous one, and you've probably had to play with your own optimization too. So this is always something that you'll need to tune, the optimizer, the step size, some other hyperparameters that, as we call them. And when we execute this, then we get nice optimization. We see that the time decreases, the path time decreases. We can also visualize the path in two ways. One is the actual path that is taken by the dog, and the other is the objective function in 2D. So we have here x1 and x2, and the color indicates how long that path would take to traverse. And we can see the optimization here, reducing the path time. Any questions so far? Yes. Which part? The. Yeah. Okay. So we have initialization. We create the optimizer, and then we run gradient descent for 20 iterations. Okay, makes sense? Okay. Yeah. So in the initial code, I wrote 0 iterations. So you had to pay attention to see that you need to set the amount of iterations. All right. So let's move on. Let's get back to where we were. Okay. So now we're going to make a small detour into the world of rendering, and we'll come back to differentiable programming to make differentiable rendering. So rendering is a process of taking some scene and drawing it onto the screen. It could be a complex 3D scene of a simulation or a 3D game, but it can also be just Super Mario or super simple 2D shapes. And it's a relatively mature topic in computer science. Of course, there are innovations all the time, including hardware, but many of the algorithms are well known and have been developed like 50 years ago. So this is an example of an algorithm for tracing a circle from a classic computer graphics book. But these types of algorithms don't have gradients. So if for some reason, which we can't imagine maybe, or maybe we can, but we'll see soon, we wanted to differentiate through the render that we just did and change the parameters of the scene, then we can do that with classical computer graphics algorithms. So first, I need to convince you that it's a potentially desirable thing to do, to differentiate through something that I render. And then we can talk about how to do that. So actually, differentiable rendering is a very hot field for the last couple of years. As far as I'm aware, it can have many uses. As far as I'm aware, there are two main sub-scenes. One is all the art in games, and if you've heard of Gaussian splatting, it's really hot these days. Just yesterday, I saw like a Gaussian splatting reconstruction of some cathedral, which is very impressive. So it's basically a new technique to represent 3D scenes that is based on differentiable rendering, and a completely different sort of application, which is actually where I'm coming from, is in the healthcare domains, creating 3D reconstructions of stuff. Okay, I specifically work with teeth, and it's a very interesting topic. So you have maybe some 2D scans or 2D data, and you want to optimize a 3D structure to match this 2D information. So this is why you might want to render something, but that the parameters of the 3D object that you render, you want it to be differentiable so that you can optimize it to match to some 2D scene. So let's start slow. Let's take it step by step. As opposed to the classical computer graphics algorithms, this is a very simple algorithm that draws a circle, that fills a circle. It's differentiable, although its gradient is not very informative yet, but it's a step. So what do we do here? First of all, we work with torch versions of NumPy, a familiar NumPy interface. So we create linearly spaced x and y coordinates. Okay, in this example, between -10 and 10, with 150 samples in between for each axis. Then we create a mesh grid. So it's just a pair of, it returns a tuple of grid of x and y, which multiplies or tiles x in the horizontal axis and y in the vertical axis. And then, so these are my circle parameters, the x center, y center, and the radius. And what I'm doing here is just a vector calculation of the distance between each point in my frame and the center of the circle. Okay, so this will give me the distance between each point in my frame and the center of the circle. So, here I compare that distance to the radius. Okay, and put the result in a variable z, okay, which will give me something like this, or exactly this. If you run this code, this is what you'll get. So each of those pixels is represented by some entry in XX and YY. And for each of those pixels, I calculate the distance first, and then threshold it by the radius. And so we get a circle, and we perform an explicit computation for each pixel. Okay, this part is important for the differentiable. So since we compute a value for each pixel, then we have we can have a gradient for each pixel. Any questions so far? All right. So it's nice that it's differentiable, but the gradient is 0 almost everywhere because we use a hard threshold. And if we want to make it usefully differentiable, so to be able to optimize through it, then this will not do. But we can make a small modification to this hard threshold. What if instead of a hard threshold, we use a soft threshold, such as the logistic function? Okay, it should be relatively familiar. It's common in many areas, including machine learning, and we can use some parameter here, or hyperparameter here, which is the coefficient of x in the exponent in the denominator, to decide how smooth or hard this threshold is. So for a very large or a very large negative coefficient, this will be a very sharp transition. And for something closer to 0, it will be very, very smooth. So very, very soft. All right? Make sense? Okay. So in the next exercise, what you're going to do is to recover the parameters of a 2D circle with this very, very simplistic differentiable rendering. Before I let you do that, there are a couple of things I want you to pay attention to. So when we optimize, especially with gradient descent, there is a concept of local optimum or local minimum. So in this case, we have a function with several, like if I start, for example, here and perform gradient descent, then the derivative points me to go to increase x, right, to go to the right. So I will reach some minimum, but it's a local minimum, so it's not necessarily what I'm looking for. And this is a major difficulty in many differentiable programming setups where you might converge to like the optimizer works, it brings you to some minimum, but it's not the global minimum. And how to avoid this is very application specific, but there are a couple of things I can recommend. First of all, there are many different optimizers, and it's something that's very actively researched. And you can go to, for example, all the dozens of optimizers supported by PyTorch. And they are based on all sorts of heuristics that have been found to be useful in optimization. So, for example, pair parameter, momentum, so-called, that changes the step dynamically based on the scales of the partial derivatives and all sorts of stuff. And if it really matters to you, then you can get into the weeds of the problem and figure out which optimizer is best. But even if not, you can play with a bunch of different optimizers and see which works best for your application. And another thing that is very important, and you'll have to take into account in this exercise, is the relative parameter scales. So take a look at this optimization landscape. So this is we have here a visualization of a 2D objective function, and darker is lower. So if you want to minimize, we want to get to the darkest areas. Now, if I start here, for example, then the gradient can point, or points in this case, in this direction, right? And it will make me converge to some local optimum. And you can do all sorts of fancy things, but if you're familiar with your loss landscape, your objective function landscape, and you can visualize it or you can reason about it, then you can just squish or expand various parameters. And this changes the direction of the gradient, right? Because the gradient is just the direction of steepest descent. So when you squish a single parameter, it makes whatever change happens across that parameter more increases the magnitude. Okay, so In this case, if I start with the same place, then I will end up at the global minimum. So it's not, you have to develop some intuition for your problem and use visualizations and think about it. But this is a very powerful way to steer your optimization from local optimums to global optimums. All right, so this is the time for the second exercise. Pay attention, there are similar helper functions for for example, in the solution, I'll use the mean squared error between each pixel's intensity and the ground truth intensity of the same corresponding pixel. Okay, who succeeded? Who finished? Nice. All right. I think we'll move on to the solution, and then you'll have more time to practice this in the third exercise, and you can also go back here and figure out what was left for you to do. So it's not trivial because there are some like hyperparameters to tune, and there can be some local optimums that we can fall into. All right. So the first thing we have here is an interactive visualization of the smooth threshold or the soft threshold that we create for the circle. So this is the logistic function, and the coefficient here that we can control is the exponent of the distance basically between the point and the center of the circle. So you can play with it, and we can see that when the coefficient is large, we have a very sharp threshold, which is almost like for a large enough coefficient, that will be very much like the first zero gradient that we had. And when the coefficient is very close to zero, it's very smooth. So the circle is much more spread out, and it's a trade-off, right? Because when it's bigger, it's a more accurate rendering. It will be more similar to the ground truth, but the gradients will be less informative. So it's a hyperparameter you'll have to tune because we want informative gradients, but we want the function, the rendering to be able to reproduce relatively accurately the ground truth. So you have to play with it. All right, here we have the rendering function. So it's very similar. It's basically what I showed in the example. So, but when we plug in the soft threshold, so we linearly sample x and y between -10 and 10, which is the extent of the ground truth image, as this visualization shows. Right? It's important to remember the grounding in 2D space of the ground truth. And then we use mesh grid to create to represent each pixel, and we calculate the distance in exactly the same way. But here, instead of just thresholding by the radius, we subtract the distance from the radius and plug that as the variable to the logistic function. Okay, with some threshold that I chose that I found to be a good balance between accuracy of the rendering and informative gradients. Okay, so we have here a visualization of the rendering, which shows the circle with a soft threshold. And any questions about this, about the rendering, before I move on? All right, so let's move on to the optimization. This involves initialization, which is relatively straightforward. So I put the center of the circle in the center of the frame at the beginning and choose some radius arbitrarily, 3. I use here the Adam optimizer, which is often also used in machine learning, with a much smaller learning rate than what we use for the SGD optimizer, the gradient descent optimizer. And here, so here's the optimization itself. We render the circle with the current parameters, and now we want to reduce that the difference between that rendering and the ground truth to a single scalar, right? So this is what we have on the next line. I subtract the ground truth from the result and square that. This is the squared error, and then I take the mean over the whole frame. Okay, so this is a 2D difference going into a single scalar, and then this is the scalar that we differentiate through to optimize. Okay, with the same pattern that we saw before. So resetting the optimizer, computing gradients, and taking a step. And if we run that, then this is the optimization that we'll see. We see the difference reducing, and no, I didn't run the initialization. We see the difference reducing, and we also see a short animation showing us how our rendering optimizes to match the ground truth. We see that at the end, it's not a perfect match. There is still some difference due to the soft threshold that we use versus the hard threshold of the ground truth, right? And we could do something more sophisticated of, for example, having a relatively small coefficient at the beginning to have more informative gradients, and then gradually, as we optimize, increase the threshold to create a more realistic rendering, okay? But that's not for now. Another thing I wanted to show is about the relative parameter scalings. So if for some reason I used a coefficient to basically stretch the center of the circle parameters, so I multiply the center of x by 0.1 and same for center of y, and so this can still represent the exact same circle, right? But instead of, for example, if the ground truth center of the circle is 3 and 5, then when I divide it by 10, it has to be 30 and 50. And in theory, that's still the global optimum, right? But if I optimize like this, then we'll see that the optimization converges to some local optimum of, okay, you want to minimize the error. I don't know, like the closest minimum is just to make the circle as small as possible, okay? So we still have all this as an error, but this is the local optimum of this problem, at least like with these optimization circumstances. So this is an example of how to create a local optimum, but in the next exercise you'll probably have to use something similar but inverse to avoid a local optimum. Okay, any questions so far? No questions. I hope that's because everything is clear and not very unclear. But let's move on. All right, so we're moving pretty fast to the third exercise, where you're going to do very much the same thing, except that you're going to reconstruct a 3D scene, okay? So we're adding a few complexities here, but basically everything is the same. So instead of 2 dimensions, we have 3 dimensions. Our scene is composed of 5 spheres in 3D space, okay? What do we have in the ground truth? So we have 3 renders, one for each projection of the scene onto a pair of the XYZ axis. Okay, so we have one projection onto X and Y, one projection onto X and Z, and one projection onto Y and Z. Okay, so that's one difference. Another difference is that we have the renders contain the correspondence between the spheres, which is very useful information. Okay, and it's not necessarily trivial to have that in a real world setting, but we know, for example, where's my pointer? We know that this circle in this projection, in the XY projection, the green circle corresponds to the green circle in the XZ projection, which gives us a ton of information, okay, and we want to use this. So in the notebook, you'll see that when we load the ground truth, we split each frame into 5 layers, okay, so the ground truth that we want to optimize compared to is also 3D, but not the same sort of 3D as in 3D space, but it has a layer for each sphere, a separate layer for each sphere, and we want to render to a similar shape, okay? And then we'll have the coordinates of each sphere, which is x, y, z, and the radius. Okay, the structure is pretty similar. So you have the log history function, so you can see what the optimization is doing, and a lot of the lessons are relevant. So the scaling of the parameters, for example, I found it very important, and the choice of optimizer and learning rate can affect. But everything else is the same. Of course, you have to also take into account the projection. So when I render how do we parameterize the problem? We have 4 parameters for each sphere, x, y, z, and r. When I want, for example, to render the xz projection, then I just do the same rendering as in the previous exercise and drop the y coordinate, okay? So we have to take care of that. All right, so good luck, and I'll move around to help you.
So did I understand correctly that this is a single scene with three views of it?
Yes, this is a single scene with renderings from 3 views, which happen to be the projections of the perfect projections along the XY, XZ, and YZ axis. And I forgot to say something important. So in the visualization, this scene is drawn from a specific angle, and the spheres encode a binary number from this angle. So the first to crack the code will win eternal glory. Good luck. Okay, let's take a couple more minutes and then I'll go over the solution so that we'll have time before the end of the workshop. Has anybody cracked the code yet? So there's still a chance for everybody. All right, let's talk about the solution. So it's not trivial at all, certainly not in like 15 minutes, even less that you had. So I encourage you to go back to it after you look at the solution and try to figure out like what was left or what were the differences. So the rendering is very similar. The core of the rendering is very similar to what we've had in the 2D case. We have a mesh grid to represent the pixels, and at some point we calculate the distance between each pixel and the center of some 2D circle, and then oh, thank you. All right. Now I hope it makes much more sense. So we have a mesh grid of pixels in 2D space, and at some point we calculate the distance between each pixel and some 2D center of a circle, and then transform it with the sigmoid. The difference, so there are a couple of differences. First of all, we do it once for each sphere, okay, and then we accumulate all the spheres in some list and stack it at the end to create layers of spheres that correspond to how we split the ground truth. Okay, this is one way to represent the fact that we know the correspondence of spheres between ground truth frames. And we have to implement the projection. So how do we implement the projection? The rendering function accepts as a parameter a tuple of axes. So this is saying which axis do we want to render the spheres from, and we pick the center of the 2D circle based on those axes, okay, from the three axes of the center of the 3D sphere. And last, what you can see here is that I'm applying very aggressive scaling to the center coordinates, and this makes it much easier for the optimizer to move the spheres around, okay? We'll see later, but when I saw that when I used equal scaling between the center and the radius, then the optimizer almost always went to a local optimum of just shrinking the spheres because moving them was more expensive. Okay, so any questions about the rendering? Yes, so you're right, that's a good emphasis. Each parameter, so the params is a 2D tensor where each row is the parameter of a single sphere, a single ball, and it's organized as, I chose to organize it as R, X, Y, Z, okay? So that's a good point. Any more questions? Cool, so let's look at the optimization. First, we have the calculation of a loss. So in the 2D case, we had to reduce a frame of errors into a single scalar. Now we have to reduce 3 frames of error into a single scalar. So we use for each frame the same reduction. So we do mean squared error, and then we average the 3 projections, okay? And you see here that the rendering is done all with the sphere parameters, and once for xy, once for xz, and once for yz. And the order here matters. So I have to pay attention to compare the rendering of the xy projection to the ground truth of the xy projection, and not to mix viewpoints, because then it'll be a mess. Okay, so this is the objective function that I want to minimize. And then we have a pretty straightforward gradient descent. So initialize the parameters. I chose to put all the spheres in the center with a radius of 2. And then we start with the optimization. I'll say that perhaps this is not the best practice necessarily. So sometimes you want to break the symmetry, because in this way the optimizer doesn't have any way to know or to choose which sphere in the parameter space will go to which rendering, to which sphere in the ground truth. But it works in this setup, it works even like this. And then we just perform the optimization. Since I used scaling in the rendering, I have to remember to factor that in when I want to use the parameters, for example, for logging the history. And then what we see is that the loss reduces, and we can get an animation of the optimization process. So on the side, we see that all the ground truth spheres get their corresponding rendering, and we can see the shape, like the viewing angle of the 3D animation gives us a binary number, 10110, which is 22. So this is the code. Any questions about the optimization? At this? Yes, sure. I also think it's very interesting. It's a very interesting exercise to take the solution and play with the hyperparameters, play with the scaling, and see how it affects the